Okay, good morning, everybody. Welcome to this course on AMD GPU programming with HIP. We're currently on day 3 of our 6-day long course on HIP programming. We'll start with a small recap of computation, and we'll be hoping to start with HIP memory today. We'll finish up HIP computation, and we'll start with HIP memory related concepts today. So I'll start with a small recap of what we have learned so far in computation. So we saw the basic concepts here about how to compile a program and how to launch a kernel, how to uh, put a barrier between device and host so that we can complete the execution of device code before the host goes out of scope in the memory. And we saw various different examples. We saw what grids and blocks are, and we saw the usage of HIP device synchronize. And we saw a couple of examples of how we can get interleaved execution when we place HIP device synchronize at different places in the code. And we made certain observations on how, based on how we can place HIP device synchronize. We saw that uh, we saw this wavefronts executing in SIMD fashion. And yeah, then we moved to memory related memory copy, and we saw that memory on host and device is different. And we tried to make a simple for loop run on the GPU. We saw the different performance gains and the performance penalties when we launch threads, when we launch kernels, when we launch multiple kernels. We saw that if we launch a lot of kernels, then we get a lot of performance penalty because of the launch overhead that comes associated with kernel launches. And then we saw that we can completely paralyze this for loop by launching 1,000 threads. And we saw how to compute the thread ID and thread ID and block ID, and then get that number inside the thread and use that to compute the square of numbers. And we explained how to calculate the globally unique thread ID for each thread. And we saw that when we totally paralyze it, we may not get the sequential output that we expect. What we saw in case of normal for loop, and we saw that this code will give a compiler error because the memory on GPU and CPU are different. And if you try to access CPU allocated memory on the GPU, we'll get a error saying that we'll get a compiler error saying that this variable is not defined on the device code. And we saw how to allocate memory using HIP-malloc and how to deallocate that allocated memory using HIP-free. We saw certain examples of how to do this. And then we saw how to copy uh, uh, data from CPU to GPU and GPU to CPU. We saw a full example of use how to totally paralyze vector manipulation operation. And then we saw an example where we actually timed the CPU and GPU execution and saw that how fast that a GPU can perform operations in parallel when compared to a CPU which has a higher clock speed but will still take much more time when it's executing in serial. We concluded with concluded that section with showing what a typical program flow of a HIP program will be like. And then we moved on to thread organization. Yesterday we started with thread organization, and we saw the data type used to specify the grid and block dimensions. And we saw 2D example, and we saw how to calculate the unique block ID and unique thread ID within a thread block. When we are, this is a image of a 2D grid of blocks and threads, blocks and grid, 2D grid and 2D block, a 4x4 grid and a 3x3 block. We also saw examples of how to use, how to do, how to use this 2D grid and block for matrix multiplication and addition of matrices. And uh, we saw that it doesn't have much of a performance penalty in both the cases. There's only a slight manipulation in calculating the index of the resultant. There's just a difference in calculating the index when we do the computation, as you can see here. In case of 2D, we calculate the thread ID x, the global unique thread ID along the x-axis and along the y-axis, and we compute the index here. And yeah, here also the number of threads launched is m into n, but m along the x-axis and n along the y-axis. In case of 1D, we launch m into n along the x-axis itself. And this is where we stopped yesterday, where we saw where we were starting with the number of where we were planning to move on to more than 1024 threads. So so far in the examples that okay, before that, does anybody have any doubts regarding what we've seen so far? Anything from yesterday's or day before yesterday's lectures which you need clarification on? You can unmute or you can put it in the chat box. Should we use device sync before memcopy? We didn't know. As far as I've seen, it is not required to put device synchronized before memcopy, because they'll go into the same queue, and once the kernel is executed, we go on to execute the memcopy. So since they go into the same queue, it'll be picked up one after the other, and we don't need to put a device synchronized before memcopy. And definitely not after it, because it's a blocking code. Okay. Now going beyond 1024 threads, because in any normal case, it is we can expect that there will be definitely more than 1024 threads, or we need to launch more than 1024 threads. And of course, block size doesn't necessarily have to be 1024. It can be less than that, but it can only be maximum of 1024. And depending on the problem at hand, we can vary the block size, and we may get more performance based on the size of the block. Say, for example, when we use shared memory, or say local data store in terms of AMD terminology, we'll have a fixed amount of local data store per compute unit. So if we have not compute unit, per work group. So in a work group or in a block, if we have lower number of threads in a block, that means each thread will have access to more local data store. Or when we deal with images, let's say we deal with 8x8 images, that means we only need, and if you are dealing with each pixel in an 8x8 image, we don't need to launch 1024 threads in a block. Specifically, we can launch like say 8 cross 8, a block size of 8 cross 8, and that would be more ideal because it fits the problem at hand. Okay, let's take an example of adding two vectors again, but here we'll have 1024 into 32 elements in each of the vectors, and we'll store it in a third vector. We'll use 1D grid and block dimensions, and yeah, you guys can take a minute or two and then see if you can solve this. This is pretty straightforward problem. Thing is that because we can't use more than 1024 threads in a block, we'll have to use more blocks. So you guys can take a minute and then try to solve it. You can post your answers in the chat box. In fact, you don't have to write the kernel. Maybe just the launch configuration is enough. The blocks and thread dimensions, block dimension and grid dimension will be more than enough. Excuse me. Yes, Viren has posted an answer where the number of blocks is 32 and number of threads is 1024. Yeah, that's correct, Viren. And Saurabh has also posted the same answer. Yeah, both of you are right. That is how because we need 1024 into 32 elements, we launch 1024 threads in one block, and we'll launch 32 of such blocks. So we'll get a total of 32 into 1024 threads in total. And it doesn't, suppose if we use a thread per block of 256, in this case, what would be the number of blocks? Okay, this is small typo here. If this 1024 is 256, what would be the number of blocks required in such a case? As in it's the same question, we have the same vector, which requires 1024 by 1024 into 32 elements in the vector. But instead of using 1024 threads per block, we are using 256. So in that case, what would be the number of blocks? Okay, Viren, you're right. Because the number of threads per block has been reduced to 4, the number of blocks will increase by a factor of 4. Essentially, we need 1024 into 32 threads. Yeah, 256. Yeah, 128, I believe it would be 32 into 4. Sort of. Yeah, you're correct. Essentially, we'll need whatever the number of blocks and the number of threads per block. When we multiply it, we should get 1024 into 32. So we can, and as I said earlier, it doesn't necessarily have to be 256 or 1024. It can be any number. But and the only thing is that AMD recommends, not just AMD, even CUDA recommends that it should be a multiple of 64, the number of threads per block, because the size of a wavefront is 64. And we'll see an example of this as we in the end of this session, where we'll deal with wavefronts. And in case of CUDA, the size of a WOP is 32, but in this AMD GPUs, it's 64. So they recommend that whatever the threads per block, it's a multiple of 64. Okay, moving on to the same example, but with little change. Here we'll be adding two vectors, and both vectors will contain n elements each. It's the same question. The only thing is that we can assume that n is a multiple of 1024, a non-zero multiple, positive non-zero multiple of 1024. In such a case, so n can be any number, but it will be a multiple of 1024. So in such a case, what would be the change? How can you calculate the block size and number of threads per block? You can take a minute or two to think about it. You can post your answers in the chat box. Yeah, both Saurabh and Viren, both of you are right. And what if? Yeah, that is correct. Both of you are given the right answers. So yes, in such a case, we'll calculate the blocks is n by 1024, and then just a minute. Yeah. Okay. I think you guys made a mistake there. Okay. I think I made a mistake in the slides. It should be n comma 1 comma 1 if there are total n elements. Just a moment. Yeah. I think the slides are correct. So there are total n elements, and if you're launching 1024 threads in a block, the number of blocks should be n by 1024. Yeah, so both of you have, I think there might have been a small confusion with the question. That is why I think you guys got the wrong answer. But so totally there are n elements, and we just know that n is a multiple of 1024. It can be 1024 or 2048. So if it is, say, let's take the example of 2048, and if you're launching 1024 threads per block, then the number of blocks should be 2048 by 1024, which is 2 blocks. And 2 blocks gives 2 into 1024 gives 2048 elements in total. Okay, now we'll move on to a little trickier question where both the vectors contain n elements and n can be any integer. So take a moment to think about for the possible solutions that you can come to. There's a little trick. There's a slight. It's a little tricky question, but you guys can take a minute or two to think about it. Okay, Viren has given an answer. I think it's n by n mod 64 blocks is n plus padding by 64 threads by 64. Plus one number of threads is 1024. Okay. Um, yeah. Yeah, Viren Saudrab and Raghavi, I think all of you are correct. So we'll see. Can we use the previous solution in this case? What do you think? Where we divided n by 1024 and use that as the number of blocks. Can we use that solution? And if not, why do you think this is not possible? Sviren has said not possible because the resultant value may not be an integer or may not be a multiple of 64 or a multiple of the number of threads per block. I'm assuming. But we are Viren, why do you think we can't? Because anyway, this will be an integer division. Say it is suppose n is say 2050. Then the integer division will give the result is two. The number of blocks is two. So why would that be a problem here? Yeah. So that is what happens when we do. When you're right, we'll run short of a few threads because suppose we have 2050 threads in total. Um, we require 2050. Say n is 2050, and we divide it by 1024. We'll get only two blocks, and two blocks will give only 2048 threads, which means that we'll not get a few threads. So how about now? What if we do this? What if we do seal on n by 1024? So that should essentially give a sealing value, right? Will this work? And if not, why would it not run? Why would it not work? The question is, can this we may need to add out of bounds logic so that all extra threads don't operate on. Everyone, you're right, but will this work? Is the question. Will this work? Can this work or will this not work? The You're right about the out of bounds logic. That is true, but right now, will this work? Will this solution work if we add a seal to the operation that we are doing? Okay, so this will also not work because when we do n by 1024, uh, when we do seal of n by 1024, uh, at first n by 1024 will be evaluated first. And the result of this will be an integer. And in case of integer division, the result will always be rounded down. So if you do, say, 5 by 3, and both of them are integers, let's say int a is equal to 5, int b is equal to 3, and if you do a by b, the result will be 1 because it will always be rounded down. Even though the floating point result will be 3.66, 1.66, the result will always be rounded down to 1. So here also, if you do n by 1024, the result will be an integer. And the same in the case of if we take 2050, n as 2050, we divide n by 2050 by 1024, we'll get 2. And if we do seal of 2, it will just be 2 again. Again, we'll be running short of a few threads. So in order to avoid this, there are multiple ways we can do this. One is to cast one of the operands to float, or obviously do n by 1024.0, which will make the denominator of floating point number. And if one of them is a floating point value, then the whole operation will be considered as a floating point division, and then we'll get some value greater than 2. And when we do seal of 2 point something, we'll obviously get 3. So this is uh, this is what happens when we deal with integer division. So this is something that we should be careful about. And there are 2, 3 more other ways to do this, which is I think Viren had mentioned that, and what Saurabh mentioned. If it's integer division, you can just add 1 and then get the proper answer. But in that case also, Saurabh, if the number of threads, if n is a multiple of 1024, then you might be adding one block unnecessarily. Say if it's 2048, and if you do 2048 by 1024, you'll get 2, and then you're adding one more block unnecessarily. So that may not be required, but in this case, that will not happen. And Viren's solution is to get the number of remaining and then add. Yes, I believe that should work, Viren, but I need to just confirm if it works. Okay, for this problem, wouldn't it be better to use 64 rather than 1024? Why, Viren, would you use 1024? I mean, 64 instead of 1024? Okay. But n can be any value, right? Like n can be something greater than 1024 as well. The vectors are okay. Creating a lot of extra threads. Okay, so if we are using 1024, and then if we have 1025 as the case, then you're saying we'll be creating 1023 extra threads. Yeah, that is true. Yeah, that is true. But again, as I said, it usually depends on the problem at hand. It is okay, like we can launch it with 64, but I don't think launching extra threads will have some penalty. Or the only problem is that in case we need a lot of threads, if we are dealing with such huge amount of data, and then we are like launching 1023 threads which are not being used, at that point it makes sense. But other than that, I don't think launching threads will have any specific launching more threads will have any specific penalty as such. But you're right, if we use 64, then in this case we'll have a lot less threads which are being unused. Okay, so coming back, incorporating this newly obtained information about ceiling and integer division, what can go wrong in this piece of code? So I've written a little more code to show you the kernel and the calculation of number of blocks. So in this case, what do you think can go wrong? Specifically within the kernel, can anything go wrong? Yeah, Viren has said out of bounds. Any other answers, anybody? So yeah, so we'll be accessing. There's a possibility that we may access out of bounds because say we have in the same cases before. Say we launch 10, we have NS2050. Number of blocks will be 3 in that case. So we'll be launching 1024 into 3 threads. But n is only 2050, and 1024 into 3 is obviously almost in the range of 3072, I guess. So we have these many extra threads. So all of them will calculate their ID, and we'll have threads like we'll have one thread with a global thread ID of 3000, and when we do C of 3000, we'll get a array access out of bounds because our arrays are only allocated till 2050. So we should always add a check to see if the thread ID is less than what we want it to be before we do any kind of memory access. And we are getting this because we're doing the seal function so that we don't get the less than the number of required threads. But obviously, in most cases, we'll be launching more than the number of threads that we actually require. And there's no workaround with this when we launch threads as such. Or maybe we can launch like one thread per block, and then in such a case, we might be able to get better, but then the performance will obviously take a hit. So we should add this check of if id less than n. So I'm passing n as a parameter to this kernel, and then I'm checking if the id is less than n. Only then I'm uh, using that index into the array. Okay. So far, does anybody have any doubts before me move to a serial to parallel example?
Matthew, quick question.
Yeah.
So if two threads attempt to write to the same location, that is, let's say a
Yeah.
location at 3, is that a problem?
Yeah, that is true. If it's the same location, we'll have a problem, which is that there'll be a data race. And if at the same time, if you're writing it, only uh, one of their writes might be visible to us. So we'll deal with this in the synchronization section where we use atomics to make sure that we get the expected output. Say if we have uh, one memory location which is allocated on the global memory, and both two threads are adding their values to it at the same time, and it is possible that only one of their operations might be visible at the end of both the operations. So we'll deal with this in detail in synchronization and how to avoid this. Yeah.
Okay, thanks.
Any other doubts, anybody? So far in thread organization or dealing with more than 1024 threads? Okay, now we'll move on to a serial to parallel example where we'll convert a serial implementation to a parallel example, parallel HIP code, and we'll time this to see how exactly uh, it performs. So we'll see an example of multiplying two matrices, and obviously the simplest possible version of matrix multiplication uses three loops. One which iterates over the row of the first second matrix, and each column. So we are using a square matrix of size 64. I've written 8 by 8, but it actually means it's 64 by 64. And for showing you the output, I'll be using a 8 by 8 matrix. And for timing, we'll use a 64 by 64 matrix. So I'll just show you the serial version of the code. This is the serial version of the code where we are using three loops. So just have a look at this, and if anybody has any doubts regarding this implementation, we can discuss now before we go to the parallel version. If I explain this code, it's pretty straightforward. The first loop will iterate over the rows of A, and the second loop, which is the JJ loop, will iterate across the columns of B. And the third loop, which is KK, will iterate across the elements of each row and each column. So when we do a matrix multiplication, we'll be multiplying the first element of the row and the first element of the column, second element of the row and second element of the column, and we'll be adding it. So yeah, this is the serial solution to this. So I'll just show you an example, and we can see the output to see if it's correct. So I've used a matrix A, which essentially show you the code as well. So yeah, here the matrix size is 8, so that we can properly see the output. And so the elements of A will be it will be the sum of the row and column indices, the elements of A. And elements of I'm using B as 2 times the identity matrix, so it'll have 2 across its diagonal. And I'm timing only the matrix multiply function call, which essentially does the matrix multiplication. It adds, it iterates across the columns and rows of A and B and A, and then adds each of them, and then stores them in the CIIJJ element. So you can see that this is the output. This is matrix A, and this is matrix B. Obviously, when you multiply it by 2i, you will get 2 times the matrix A. And yeah, you can see that the time taken for multiplication here is 0 microseconds, because obviously this is a rather small matrix, and on CPU, which has a very high clock speed, it'll take it'll take even less than 1 microsecond, even less than 0 microsecond. So it'll be in the order of maybe nanoseconds. So now we'll see a bigger example where we are using a matrix size of 64. So I've made a few changes here, which is that I'm not printing the output because the output would be too, we will not be able to see the output properly. So yeah. And you can see that in case of 64 by 64 matrix, it'll take 123 microseconds for the entire serial matrix, for the matrix multiplication to happen in a serial setting. Okay, so we'll move on to the parallel version. So we'll start parallelizing and we'll think of how we can introduce parallelism here. And is it possible that we can remove one of the for loops that we have here? You guys can have like just think about it and maybe think about how we can remove one of the for loops, either the outer or the inner or the middle for loop. Maybe take 3 minutes and you can put your ideas in the chat box. You don't have to write the code, but yeah. Wherein saying innermost for loop k could be removed. Kernel gets the ij of Million is saying we can remove the inner loop. Kernel gets ij of the output matrix's arguments and implementation argument difficult to compute. Uh, so if you are giving ij as the matrix arguments to the kernel, is it Million?
Yeah.
So how would we vary ing then? We need to vary ing, right?
As in, so let's say if the A is M into N and the B is N into P. So M into P will vary two indices between M and P, the inner and the outer loop, and I and J belong to any one of these combinations. So for every element in the output matrix C, it just has to access the corresponding row and column from A and B. So it's
So
independent.
okay, so from this, let's assume it's a square matrix, and so we'll be passing ing as. When I say we're parallelizing, we'll have to move this into the kernel itself. So we'll be dealing with more kernel launches in such a case, right?
N square kernel launches, if I understand it correctly.
So you'll remove the. Okay, can you repeat your solution once again?
Okay, so the essential idea is that for every element, computing every element in the output array is independent of the other element in the output array. So if I can give the kernel a single task of computing I comma jth element of the output array, and how it does is given it has if it has access to, let's say, the ith row and the jth column of A and B. That I think. Okay, excuse me, folks.
Okay, so total n square elements you launch.
N square threads.
So only the inner loop,
Inner
except
loop gets
you're
removed. Yeah.
removing the inner loop.
Okay. The assumption here is that A and B are small enough, or they are stored in a global memory that all the kernels can have an access to. That's a very big assumption here.
All the kernels or all the threads?
All the threads. Okay, sorry. All the threads have an access to a global memory, and A and B both fit into whether it's a global memory or the local memory.
Okay. Okay. So that would require, and again, you're removing only the inner loop and both the outer loops.
That's correct. Yeah.
Okay. Okay, I'll have to look into that solution. Maybe Milian, if you can write the kernel and send it to me, I can have a look.
I'll give it a try.
Yeah.
Thanks.
Okay. So we'll start with removing one of the for loops, and I'll be dealing with removing the outer for loop first. So here, what we're doing is instead of iterating over each row of A, what I'll do is I'll launch n threads such that one thread will deal with one row of A. So if you see here, II is now being computed as the global thread ID of each thread, and we'll be using that II instead of using a for loop to iterate over II. So II will range from 0 to n, 0 to matrix size. Obviously, because the matrix size is 64, it will be in. We have to do that boundary check here as well, but let's just assume that we are handling it somewhere. So and the II will range from 0 to 64, which means that 0 to 63. So II will have all the row IDs. So it'll be same as iterating over each of the rows, and but all that will happen in parallel. And if you see, there is no data dependency as such, because I into matrix plus JJ will always be different for each of the uh, threads, each of the 64 threads that we are launching. Does anybody have any doubt in this solution? Okay, so yeah, here we have parallelized something. At least we are dealing with all the rows of A in parallel, and we'll see what the output is in this case. So the same code is for it's almost the same code. Only thing is that we are adding a dummy kernel launch so that we can warm up the HIP instance, so that our timing is not it doesn't affect the timing, and everything else remains the same. We are launching the kernel here with 8 threads in this case, and we are doing HIP device synchronize so that we can get the complete time we require to compute the matrix multiplication, and then we are copying it back and then printing the result. So, and it's the same matrices. The elements of A will be the sum of the indices of each element, and B will be 2 times the identity matrix. So we can see that the output is the same. We can see this is the identity matrix, and this is the other matrix A. And the time taken for this multiplication is 31 microseconds when we compare it to the previous one. Of course, this is the smaller version, and in case of CPU, we got it in less than 0 microsecond, less than 1 microsecond. So yeah, you can see that for smaller versions, smaller input sizes, the result takes more time on GPU. Now we'll deal with the and in case of, we'll time this for bigger, larger matrix size. Here also there is not much changes. I've added the uh, code for forming the HIP instance, and we are launching the threads per block will be matrix size here, because matrix size is 64. We can launch 64 threads for each of the rows, and so each block will have 64. But yeah, we'll in the next step, next iteration, when we make it more parallel, I'll show you how this will be a problem here. So we'll run this code to see how it performs. And we can see that it took 661 microseconds. So on CPU it took I believe 123 microseconds, and on GPU it is taking 661 microseconds. So can we make it any better? So that's the question that we have, because obviously this kind of performance is not that great for us. So we need GPUs to perform much better. So can we parallelize even more? That is the next question, which is that can we remove another for loop? So before we move on, we'll take a small break. Does anybody have any doubts in what we've seen so far in parallelizing the for loop, or anything that we've seen so far? Okay, so far, how much have you heard? Till what have you heard? We joined around 10:89. Saurabh, should I repeat any concepts? What all have you missed? I can give a brief recap if you need me to. Yeah. Wherein yesterday's, I think it has been uploaded uh, in that same folder. It will be there as code examples. You should be able to access the code snippets. I'll upload today's one as well. Yeah. Okay, so if there are no doubts, then we'll break till 10:35, and we'll continue with how to parallelize this further. So we'll resume at 10:35. Okay, so I'm hoping nobody has any doubts and everybody has understood everything so far. And regarding, it is possible that we can remove the second for loop. We can launch n threads for each of the columns of B. That's possible. But when it comes to removing the innermost loop, which is the K loop, I think we may face some issues. So if we are launching n square threads for each element of both matrices of A and B, and we are iterating, and each kernel will be iterating over II and JJ, which is the columns and rows of A. We might be facing an issue when it comes to atomics. We may face data race is what I think will happen when I'm thinking of it right now. Actually, it requires a little more thought. I'll clarify it. We'll clarify it tomorrow. During the recap session, I'll clarify it. But so far from what I can think, if we launch it for n square threads, multiple kernels will be updating the same element of the output. Like CII JJ will be updated by multiple uh, kernels, multiple threads, and this may in fact cause data race issues, and we may not get the right answer. But we can in fact change. We can in fact remove the inner loop. Like instead of removing II, we can remove the JJ loop and launch it for the n columns of B. That is possible. Okay, so we'll move on to the even better optimized version of it. Is that can we remove another for loop from this? And based on the clarification that I just gave regarding data races, I think the only other possibility would be to remove the JJ loop. Now, is it possible to do that? And if so, how can we do it? Just take a moment to think about it. You can post your ideas in the chat box. Control the II loop with blocks and JJ loops with threads. Um, okay, but so right now the II loop is dealing the rows of A and JJ with the columns of B, and both the number of rows and number of columns are equal because it's a square matrix. So, but if you're controlling it with the blocks, then if you mean the block ID, then we may not have that many blocks, right? And if JJ with thread IDs, then yeah, won't we have only have less number of threads to deal with the columns, the rows of A. Viren, can you clarify this? Like, what do you mean by controlling the II loop with blocks? Okay. Okay, so we'll see how we can remove another for loop. So this is how we do this. So just take a moment to look into this, and it might be a little confusing at first as to what is happening with I by matrix size, ID by matrix size, and ID mod matrix size. Of course, there is a mistake in this slide as well. I need to correct that. Which is that we should launch this matrix with this kernel with n square threads. I'm launching it only with n. Of course, when we launch it with n square, we are assuming that it's less than 1024. For the time being, we'll assume that. And in the live example, I'll show you. Okay, we'll see if this works or not by running it and checking if it works. So I'll show you the code for the same. First, I'll show you. We'll run the 8 by 8 matrix, and here we're doing the same operations. For II, we are calculating ID by matrix size, and for JJ, we are doing ID mod matrix size. And yeah, the hip warm up. This thing happens here. And the number of threads per block I'm using here is 256 threads per block. And the number of blocks is, of course, matrix size into matrix size plus 2. So this is another way to calculate the number of blocks that we require, which is if we have a total requirement for n threads, and we are launching 256 of them, we can do n plus 256 minus 1 by 256. So it's kind of a formula which we can employ to do. So I'll just type it up here. Suppose if we have int block num as say k, and we can calculate in number of blocks. Sorry, number of threads per block. Thread. Okay, that variable is already defined, so I'll comment it out as k. Then the number of blocks can be calculated as k. Sorry, and we need a total of n threads. We can calculate as k n plus k minus 1 the whole divided by k. This is another way to do it. You can check it out to see that we don't need the ceiling or casting to float operations here. So in a sense, we are launching n square threads here, which will be yeah, we're actually launching more than that. We are this will eventually come out to be 1 because our matrix size is 8. So this will just come to 1. So we are launching this many threads, and of course we have to do the check to see if it's less than the matrix size. So we'll just run this and see how it works, if it works. You might get some. So yeah, again we can see that the time taken for the matrix multiplication is 31 microseconds. I think it's almost similar to what we saw in the previous case. Now, one other observation that that I have to make here is that in our previous examples, we did not copy the resultant matrix, which is that we are initializing C to 0 and on the host, and then we are copying this C into the device copy as well. Now, any idea why we would be doing this? Okay, Saurabh was asking what is n over there. So n is a n in which case? Okay, this I've written right. In this case, it will be matrix size or matrix size into matrix size for this example. This I made this as a general comment. Like if we require n threads in total, and we are assigning k threads into one block, in such a case, we'll need n plus k minus 1 by k blocks. Okay, so coming back to the question, so why do you think I did this mem copy of C into DC? Usually in our yesterday's example of vector addition, I only did copy A and B. I did not copy C. Any clue as to why we did not, why we copied C in this instance? Okay, so the idea is pretty simple, is that we are doing C plus equal to something. So we should make sure that it is initialized to 0. And since on the host we've initialized it to 0 using this, we're making all the elements as 0. And then we are copying it into the device vector as well. So here C will contain all zeros initially. Or else if we don't initialize this, what happens is it is possible that we may get some garbage value inside it, and we'll be adding the product of this into that garbage value. But yesterday when we did dealt with vector addition, we were directly assigning C of I is equal to A of I plus B of I. So even if there was some garbage value, it wouldn't have affected us because we are directly assigning it and we are not doing a addition over the existing thing. That's just a small observation that we have. Now we'll move on to the timing of this thing. And here, obviously, we have to do the, it's the same thing. And only thing is that the matrix size is now 64. And we have both the I and JJ loops removed. So now let's see if this actually gives any benefit. You can see that it took 40 microseconds, and compared to the parallel 1 version, which took 662 microseconds, and we'll compare it to the serial version as well, which took 116 microseconds. So when we remove the final for loop, we got a performance which is better than the CPU version. And with 2 for loops existing, we can see that it was much worse than the serial version. So this is the benefit that we get from parallelizing existing serial code, and not all pieces of computation, or not all algorithms are parallelizable in nature. But whatever we can, if we can extract parallelism, then we can get a lot of performance gain from doing so. Does anybody have any doubts, especially with calculating the index of I and JJ? So essentially, ID will range from 0 to 64 square. And when we divide it by matrix size, we'll get all the values from 0 to 64 for II. Similarly, when we do ID mod matrix size, okay, Saurabh is asking, can you explain it again? Saurabh, is it specifically the index part or the whole algorithm? Okay. So, like I said, okay, there is a typo here, which is that we should be launching it with n square threads. And suppose we have, I'll talk about it from a general perspective. So the ID will range from 0 to n square because we are launching n square threads. We're just assuming that everything resides within one block for now, so that you can understand it. I can explain it more easily. So, so when we launch n square threads, we'll have the ID of each of these threads range from 0 to n square. Now, matrix size is the value of matrix size is n. So when we do ID by matrix size, for different threads, ID by matrix size will be different. So ID by matrix size will be something around n square by n. And because it's an integer division, it can be any number between 0 and n. So suppose if ID is 0 for a matrix, a thread, so I will come out to be 0 because we are dividing 0 by n. And if it's 1, in that case also it will be, it will, so for all IDs from 0 to n, 0 to n minus 1, the II value will be 0. Now, as soon as we reach n, say the ID is n, and as I said before, ID can range from 0 to n square. And n is between 0 and n square. So as soon as id for thread hits n, at that moment from n to 2n minus 1, all those threads will have ii value as 1. So that is with I, and it'll go all the way till n square. In which case, when the ID is n square minus 1, it won't go till n square. It will be n square minus 1. That will be the last thread ID. And when we do it n square minus 1 by n, we'll get IIS n minus 1, if I'm not wrong. Yeah, n minus 1 will be the last value of II. Now coming to JJ, JJ is what we're doing is we're doing the remainder operation. So for JJ, say if we have thread ID as 0, and we are finding the remainder when we divide it by n, in that case it will be 0. But when the thread ID is 1, we do 1 mod n, and we get JJ value as 1. And similarly, for all values from 0 to n, we'll get the remainder as 0 to n itself. So for if we have ID as n, then JJ value will be n, because n mod n square will be n mod n will be 0 in that case, and n minus 1 mod n, which will be ID is n minus 1. In that case, we'll get JJ value as n minus 1. So the remainder operation when we divide by n will always range from 0 to n minus 1. Yeah, 0 will be for when the numerator is 0 or a multiple of the denominator. Yeah, so with this we get all combinations of, so II will range from 0 to n, and JJ will also range from 0 to n. And because of the fact that with this we'll get all the combinations that we require. We'll get one of the threads will have II as 0 and JJ as 0. Another thread will have II as 0 and JJ as 1. And so all the combinations that we require to deal with both the rows and columns of JJ, we can obtain from this. So does that clear your doubt? Okay. So can we remove the final for loop? Like, is it possible to introduce even more parallelism? It's something that we can think about, but as what I can think right now, it is not possible to do that unless we employ some sort of atomics, maybe. Although I've not seen such a implementation. If you have any idea, you can we can discuss it. Where we remove the final for loop, but we can introduce more parallelism, or we can improve the performance by using techniques like tiling or shared memory. Shared memory will be, I'm hoping to start it today, but I'm not sure if we have the time. So, and tiling is one of the one of the ideas where we use shared memory, where we actually process a chunk of the matrix. And yeah, we have such techniques which we can extract more parallelism or improve the speed. Okay, with that, we'll close the serial to parallel example, and we'll move to wavefronts. So again, wavefronts are just a set of 64 threads which execute in SIMD fashion. And all these threads are totally synchronized. Like, they only look at one instruction, and all of them either don't do anything or execute that instruction. Like, if a certain thread in a wavefront cannot execute that instruction due to some condition, say, in that case they'll just not do anything. And so threads within a block are executed as wavefronts. So because all these execute in SIMD fashion, threads within a block, they'll be scheduled as wavefronts only. Like, even if you only need one thread for some execution, 64 threads will be used, because that's how it is designed. And suppose if a wavefront stalls, which is that it is waiting for some IO, then the compute units can easily switch to another wavefront. That is how it is designed. So we'll see what happens when we have wavefronts with conditions. So this is a pretty simple code. we are assuming we have less than 1024 threads. This kernel is launched with less than 1024 threads. And if named each of the instructions as instruction 0, and we have instruction 1 here, which is that it is checking if the thread ID is odd number, and if so, we are assigning AF ID as ID, and if it's an even number, then we are doing ID into ID and assigning it to AF ID, and then we are doing AF ID plus plus. We are just incrementing that value anyway. So the in the output it will be of the final output of AF ID will be either ID plus 1 or ID square plus 1. So that's the main idea of this piece of code. So, like I said, let's assume that we are dealing with one wavefront, 64 threads. All of them will look at the same instruction. So first, all the threads will look at instruction 0, which is that they'll compute their own thread IDs and store them in their local memory. And then next, it will come to instruction 1, where all of them will check if their thread IDs is an odd number. But instruction 2 can only be executed by threads which satisfy that condition, which is ID mod 2 is equal to bit 1. And instruction 3 will also, I believe it will also be executed by all, it will also be read by all the threads, but I don't think everybody will execute it, because only those threads which do not satisfy the first condition, which is the instruction 1, all of them will go to instruction 4, which is all the even numbered threads will see instruction number 4, while the odd numbered threads do not do anything, because they all have to look at the same instruction. So even while the odd numbered threads are executing instruction number 2, the even numbered threads will just wait. They can't do anything because all of them have to look at the same instruction, but they can deal with different data. And then finally, instruction number 5 is executed by all the threads, because yeah, there's no condition as such for that. So when if threads of a wavefront do not satisfy a condition, those threads will execute what we call as a no op instruction, which is that they'll just not do anything. They'll just stall. They'll just wait. They won't do anything. So here is a pictorial representation of a case where we have I've not put all the 64 threads in the wavefront. I'm just using just 4 threads. And this is the same program that we saw earlier. So I0 will be executed by all of them. Instruction 0 will be executed by all of them. And instruction 1 will be seen by all of them. But only threads 1 and threads 3, the odd numbered threads, only they can execute what is inside the if statement. So at that point, thread 0 and thread 2 will execute what is this gray rectangular box represents a no op instruction. And then they'll come to the I3, which is the else part. And if instead of an else, if it was another condition, say if ID mod 2 equal to 0, then all of them will definitely see that instruction. But when it comes to, and execute that instruction as well. But when it comes to the next statement, which is AFID equal to ID square, only the threads which satisfy that condition, which is T0 and T2, can execute it, while T1 and T3 do not do anything. And then finally, we come to I5, which will be executed by all of them. So when different threads of a wavefront are executing different instructions because of these conditions or switch statements, then and some of them are not doing anything, these threads are set to diverge, which is that one set of threads will be doing something while the other threads are not doing anything. And in another situation, these threads will not do anything while the other threads, which were doing something else earlier, was doing something. So threads which satisfy the conditions, they'll execute together, and the threads which do not satisfy the condition will execute a no op. So this essentially adds sequentiality to the execution, because obviously, if it would be better if if instead of I4 and I2, if you put them together, if we can put I4 here and I4 here, then we can see that we can eliminate this whole step. So this essentially adds sequentiality to the program. So suppose if we had four different conditions, which is that let's say id equal to 0, then do something, id equal to 1, then do something, and till 3. Then we could see that while t0 does something, all of them will stall. While t1 does something, all of them will stall. So it's essentially making the whole process sequential. The number of steps required to complete this whole execution will be more. But does it always add sequentiality is a question. So if we add conditions always, will it always have, will the threads always diverge? That's something you can think about. So when different threads within a wavefront give different truth values for different conditions, the overall execution becomes sequential. So this problem is called thread divergence, and it actually causes problems because it gives performance penalties. Now we talk about a concept called as degree of divergence, which is degree of divergence is the number of steps that is required to complete one instruction for each thread. So if there is no thread divergence, then the degree of divergence is 1. And for a fully divergent code, it will be 64, which is that, let's say thread 0 is executing something while all the others are waiting. Then thread 1 is executing something while all the others are executing in OOP. So that essentially adds, like only one thread is executing at a time, and that will essentially mean that the degree of divergence is 64. Like we need 64 different steps where only one thread is executing. Now, just a small question, which is, can you write a kernel where the degree of divergence is 4? Let's say we are launching and that kernel with 64 threads. Can you think of a kernel which has a degree of divergence is 4? Take 2-3 minutes, and you can put it in the chat box. Just maybe even the condition is enough. You don't even have to write the template part. Okay, so degree of divergence is, so in this example, the degree of divergence is 2, because say a set of threads are doing one thing while another set of threads are doing nothing. And in the else part, the other set of threads are, again, the threads which executed earlier are waiting, and the threads which did not execute are now executing. So here, essentially, you can see that there are two branches coming out. So one branch does something, and while the other branch waits, and then the other branch does something while this branch waits. So essentially, the control flow has diverged into two paths. So this is called and we use this degree of divergence as an indicator of how much sequentiality has been introduced in the code. So in this case, the degree of divergence will be 2, because we have two branches. And if we only had, say, in any other case, if we did not have any, let's say if instructions 1 through 4 is not present, then and only instruction 5 was there, then the degree of divergence is 1, because there is no divergence as such. Okay, I think Viren has said if, else if, else. Yeah, that is true, but we need the condition, and I think condition has been given by Praveen. Praveen, that's right. If id mod 4 is equal to 0, 1, 2, and 3, we'll have a degree of divergence as 4, because, yeah, correct. Viren, you're right. So yeah, which means that 64 by 4, which is 16 threads will execute the first condition where n mod 4 equal to 0, and then in the next cycle 16 will execute the else if remainder 1 part, and that keeps on happening. And finally, we'll close this section on warp or wave fronts with this small switch statement. What do you think the degree of divergence is for the below switch statement? You can take a moment and then put the answer in the chat box. Of course, the number of threads will be less than, it'll be 64. We'll assume that it's 64. Okay, Viren is saying 5. Raghav is also saying 5. Does anybody have any other answers? Okay, so the answer is 5. We will have 5 different branches because so switch ID, all the threads will look at the switch statement initially, and the case 0 will only be executed by the one which has thread 0. All the others will stall at that moment. Then the next instruction, case 2, will only be executed by thread ID 2. And similarly for 4 and 8, and all the rest of the other threads will execute the default statement. So with that, we come to the end of computation, and we'll start memory today. I don't think we'll have enough time to finish it. So yeah, we'll start with the introduction to memory today. Okay. So we'll have a quick recap of what we've seen so far in memory. So we saw that host and device do not share the same memory, which means that we can't use the same variables on host and device. There is one small exception where we can use the same variable on host device with something called as unified memory. We'll talk about that in one of the coming slides. So, and because of this different memories, we need to maintain different copies of the same data on both the host and CPU, host and device. I made a small typo there. And then we saw HIP memcopy operation, which helped us transfer data from device to host and vice versa. And memory copy operations are usually very slow, and they should be used very carefully. Like if you use it a lot, if you use memcopy a lot of times, unless it's absolutely necessary, this will have a huge performance penalty. So use it only when it's required. But there are situations where we need to use it. Say if we have SSSP implemented parallelly, I think we'll have to copy the modified array back and forth for each cycle. So yeah, there are situations where you can't avoid it as well. So this is a memory hierarchy of AMD GPU. It's a little different from what NVIDIA has. So you can have a look at it. We have the global memory, which is the VRAM, and then we have an L2 cache, which is shared across work groups. And then within each work group, we have an L1 cache, which is accessible to all the threads within that work group. And then we have something called as a local data store, which is also accessible to all the threads in that work group. And then we have local memories for threads. We have registers, and then we have local memory, which is what stores the variables. Like if you do int I is equal something, like if you saw here, we are doing int id equal to thread idx. This will go to the local memory of each thread. So that's a private local memory. So we'll see each of this in detail. So first, we'll start with global memory. So global memory is what we call as VRAM, and it is shared across all the CUs, and all the threads can access this. All the threads can access this memory. So, and VRAM is the main medium of access between the host and device. So, in fact, this image is actually incomplete. We can actually have a host. So, this is the whole device. We can have a block for CPU as a host as well, and that host memory will be connected to this global memory. I've actually omitted that here. So this acts as the main medium of communication between host and device. So when we do a memcopy operation, it's copied from the device CPU VRAM to the GPU VRAM, and it has the longest access time amongst all the all the memory available in the hierarchy. And usually it's in the range of a few GBs. Like if you see any consumer level graphics card, you'll get something from 2 GB all the way to I think 8 or 16 GBs is what we see nowadays. Consumer GPUs. And that's about it with global memory. It's quite large. It's the largest among all the memories available in the GPU. Then we have what is called as an L2 cache. So L2 cache is shared amongst all CUs. Again, all threads can access this L2 cache, and it is managed by the hardware. Like we can't allocate memory on the L2 cache. So if you're familiar with the caching mechanism that we learn in computer architecture, so it is used so that we don't have to frequently visit the slower global memory. So that is why we use L2 cache. So before accessing the global memory, the GPU will check inside the L2 memory to see if whatever it is trying to fetch is in the L2 memory. So L2 memory is smaller, but it is faster than the global memory. But it is larger than the L1 cache. Again, I've made a typo there. So usually the size of L2 cache ranges from 512 KB to 2 MB in the GCN architecture. So that is L2 cache. So that is the next, like after global memory, that is the next memory element that we talk about. Then we have what is called as an L1 cache. So L1 cache is also shared amongst all threads in a work group. Like only within the work group or within a block, L1 cache is accessible. Not all. Like if a thread from block 0 cannot access the L1 cache of block 1, and this is also not programmable by the user. So L1 cache will cache all the access that we have to global and local memory. So again, this is used for our performance benefit. So L1 cache, if you're accessing a variable frequently, then it will be cached in the L1 cache. If not, and if the L1 cache is full, then it will be spilled to the L2 cache. So before accessing the L2 cache, like before checking if something is available in the global memory, it will check the L2 cache. And before checking the L2 cache, the GPU will check the L1 cache. And there are different types of L1 cache, which is scalar cache, texture cache, and a vector cache. And we usually, when we talk about L1 cache, we say it's a vector cache. I'm not very sure what a scalar cache or a texture cache is. And it is obviously smaller and faster than an L2 cache. And it comes to around 16 kilobytes in the GCN architecture. And we have something called as a local data store. So LDS is what is shared. Again, it is shared across all the threads in a workgroup. But this memory is programmable by the user. And those of you who have used CUDA, you know what shared memory is. So LDS is similar to shared memory, but the only thing is that in NVIDIA GPUs, the shared memory and L1 cache, they share the same physical storage. And you can actually create a split between them. Like you can say that, okay, 34 KB I'll allocate for L1 cache and 32 KB I'll give to my shared memory. But in case of GCN architecture or in NV GPUs, Both of them are separate physical memories. So you get 64 kilobytes of local data store or shared memory in the GCN architecture, and a separate L1 cache which is used for caching and the whole memory hierarchy thing. So you can see that here it is two different memory elements, one L1 cache, which is directly connected to the L2 cache. And then we have the local data store, again, which is common to all the threads, and these threads can directly access it. And we'll be actually seeing how to deal with shared memory. We can allocate shared memory dynamically or statically as well. We'll see all that probably not today. So yeah, this is what local data store is, and local data store is also much faster than accessing the global memory. So we can actually gain a lot of performance. We can speed up our operations if we use shared memory more. And coming to local memory and registers. So each thread has its own local memory and a set of registers. So registers are obviously the fastest memory storage, and they are usually very small. And we use registers usually store the variables which are frequently accessed, like loop counters. Like when you iterate over a loop, we do int i's equal to 0 to some value. Those variables are frequently accessed in each iteration of the for loop. So those variables will be frequently accessed, and we store them in registers. So when we don't have enough registers to hold all the variables that is local to a thread, so obviously when we execute, when the program runs, it tries to store everything in the fastest memory possible. But sometimes we don't have enough registers to store all the variables local to a thread. So these are spilled to what is called as a private local memory. And this private memory is usually implemented in the global memory, and it will be cached in L1 and L2 caches. But the thing is that private memory of a thread, even though it is in the global memory, it cannot be accessed by other threads. Like say, if, it is private to that thread itself, even though it is in the global memory. Like we mentioned that global memory is accessible to all the threads, but local memory, even though it's implemented on the global memory, private local memory of a thread will not be accessible to other say threads. And this is something that we have to keep in mind, is that when we have when we're passing say pointers to other functions or other kernels or other threads, if we're passing some these pointers to local memory objects, we may get a problem, because these are private local memory, and we shouldn't ask other threads to access another thread's private local memory. Again, each compute unit has 256 kilobytes of register file storage. And depending, we can't say how much registers will be assigned to a single thread. It can vary depending on the number of threads currently active on the CU, or things like that will obviously come into picture. Then we have some specialized memories called as texture and constant memory. So texture memory is optimized for spatially coherent access patterns. Like say if we have neighboring threads accessing neighboring data locations, say if you're familiar with the convolution operation, then we access all the boundary pixels as well. So in such cases, we'll use what is called as texture memory. Although we don't use it that much, like I've not seen it being used, but it is something that is available to us. And then we have constant memory, which is optimized for situations where, like if all the threads read from the same location, then we can put it in the constant memory, and it is optimized for such situations. Say if you're familiar with the Saxby operation, or when we have say some computation which has the same coefficient, say we're computing ax squared plus bx plus c for different values of x, which are stored from say different in an array. A, B, and C can be made as constant memory because all the threads will be using the same A, B, and C. and it'll be better than it'll be faster and it'll be optimized better than when we do it as a global memory or when we pass it as a parameter. So we'll see more about texture and constant memory at the end of this session on memory. We'll see a few examples. And with that, we'll stop for today, and we'll continue memory tomorrow. And hopefully, I think we are getting a little delayed with respect to what we were supposed to start synchronization tomorrow. But hopefully, we'll finish up memory tomorrow and then start synchronization tomorrow itself. We are a little bit delayed, but I think we can use the reserve day to finish up the pending things. Okay, so if any of you have any doubts, I'll be here. If not, you guys can actually, yeah, take leave. Okay, does anybody have any doubt? You can unmute and talk or put it in the chat box. A grid block dimension short. Sudhanshu, which exactly, what topic are you exactly talking about when you say grid block? The 2D grid block case, is it? Oops, okay. Sudhanshu, this is what you are talking about? Okay. So when we come to calculating the global thread ID of any, like, as I said, the thread ID is unique within a block. And but as we've seen, we need a globally unique thread ID so that we can use it to access array and access arrays and deal with different data items. We need a globally unique ID. So how do we calculate it? So we calculate it using this formula, and I'll explain how exactly this formula works. So assume, even though this looks like a 3D, 2D structure, assume that we place all these dots in a single line. And if we just, so we'll have block 0, thread 0 till block 0, thread 7, and then block 1, thread 0 till block 1, thread 7, and so on. So, but if we just count the threads, we'll have thread 0, thread 1, thread 2, thread 6, thread 7. And then after that, we'll have thread 8 and thread 9 all the way till thread 31. In this case, because we have 8 into 4, 4 blocks of 8 threads each. So how does this, if we order them sequentially and then count them, we get a unique ID. So how can we get that unique ID from this block ID and thread ID? That's what we are trying to deal with here. So, so what exactly this equation does is, so we know that the block dimension is 8, which is that the size of the number of threads in each block is 8. And then we are multiplying that with block IDX and then adding thread IDX to X. So when I say my block ID is 1, what exactly does that mean? So it means that right now I'm at block 1, and before that I had block 0, which is that, so I've already seen a block, and now I'm in the block 1. So when we say that we've already seen block 0, that means, and since one block has 8 threads, when I've seen one block already, it means that I've seen 8 threads already. So right now when I'm saying I'm at block 1, that means I've seen 8 threads of block 0. And now let's say I'm my thread ID. I'm dealing with this block 1 thread 4. So when I say I'm at block 1, that means I've seen 8 threads of block 0, and then I've seen 4 threads of block 1, which are these 4, and right now I'm here. So based on this idea, like this is what this equation essentially says. So what is my current block ID? So this first part of this equation, blockdim.x into blockIDx.x, says that what is my current block ID and what is my current block dimension. So I would have seen that many threads of like I would have already covered that many threads of the previous blocks. And when I add threadIDx.x, I'm adding the number of threads I've seen so far in the current block. So when I say seen, I'm just like it is from the perspective of calculating the globally unique thread ID. So it's not like we see the threads one by one, but for one thread, how exactly we calculate the globally unique thread ID. Now let's take this block 3 and thread 2. So when you say block 3, that means that we have seen block 0, block 1, and block 2 so far. So we've seen 3 blocks. And since each of these contained 8 threads each, we would have seen 24 threads from previous blocks. And because we're dealing with thread ID 2, thread 2, that means we've seen 2 of the threads from my current block. So which gives a total of 24 plus 2, 26 would be my globally. I've seen 26, 26 threads so far. And so that means that because we have a thread ID 0, that means my current thread ID would be 26. Sudhanshu, does that explain? I mean, did you understand? Okay. So that's great. Okay. Any other doubts, anybody? Okay, if there are no other doubts, we'll close for today and we'll meet tomorrow. So thank you all for joining. See you tomorrow.